Hello everyone and welcome in my new video demo. My name is Zoran and today I will show you Modular AI voice platform and demonstrate how this works. Whenever I work in real projects like this one, I try to, whenever possible, to turn my experience into practical showcase and present in the video. The goal is to give you some ideas, solutions for your own challenges. So what you're seeing today is not just a concept or PowerPoint slides. It's a piece of a real solution I have actually used in practice. I wanted a solution that easily adapts to a wide range of needs, and I will show you later how this system works. One of the biggest challenges for modern AI systems that work with voice is noise. And by noise, I don't just mean background sounds. It's everything people unconsciously slip into their speech. Long pauses, stuttering, digressions, unclear questions, and all those little filler words that can easily throw off a model. Typical voice AI agents often either skip parts of a question or try to answer something that wasn't even a real question in the first place. The result? Wrong. Hallucinated answers and frustrated users. I addressed this by introducing an extra agent dedicated to segmenting and normalizing every input before it's sent further down the pipeline. Specifically, this agent can cleanse up the transcript first. It separates what's an actual question from what's just noise, ignoring all the wait, well, you know, and similar. Segments and normalizes the input. If a user asks multiple questions at once, which is the part of same context, the agent semantic synthesis, taking all the relevant details from the user's input and creating a single, clear, meaningful query, so each one can get a clear, precise answer. Focuses on meaning and context. It doesn't let unclear or incomplete queries go further. Everything passed on to the next services is already cleaned up and easy to understand. Together with the orchestrator guarantees order and auditability. Every answer goes exactly to the question it's meant for, with no improvisation or lost context. The result is, even if a user sends in a noisy, spontaneous voice message, the system provides a clear, accurate, and relevant question for a real-time voice model. No wasted time on misunderstandings and no frustration. This layered approach, with an extra agent for segmentation and normalization acting as a filter and interpreter, gives my system a level of robustness and reliability that the typical voice agents just can't match. To truly understand why this platform is flexible, robust, and ready for real-world use, let's look under the hood at how the components are connected and the role each one plays. First pillar is speech-to-text service, also called STT. Whether the input is from a microphone or loopback, this service uses proven cloud models like Microsoft Azure Speech to convert your voice to text in near real time. Second pillar and most central is the orchestrator, the platform's central nervous system. The orchestrator does not just pass along messages, it creates and manages all sessions, assigns a unique identifier to every conversation, and strictly enforces FIFO logic, meaning first in, first out. If multiple users are interacting in parallel, or if a single user asks several questions at once, the orchestrator keeps a separate queue for every session, making sure nothing is lost or mixed up. Third pillar, I called Agent 1, the artificial intelligence brain of the system. For this showcase, I'm using a group of models and agents deployed via Microsoft Foundry, simply because it made the implementation faster and easier. But really,
This could be any platform that offers model services. In my real-world project, the client actually used local models, running everything on their own infrastructure for a higher level of security. So generally, Agent 1 analyzes each transcript, performs what's called semantic synthesis, taking all the relevant details from the user's input and creating a single, clear, meaningful query. Filters out unnecessary information and, most importantly, can rely on specific knowledge bases, whether in the cloud or stored locally on your computer or USB drive, if privacy is a priority. This is a big difference compared to typical voice bots, which might try to pull out every individual question and answer them separately, but often get things wrong, lose context, or mix up the intent. Agent 1 acts strictly according to defined instructions, which you can change in the user interface without redeploying. Depending on the instructions you give, Agent 1's role can change. It might simply triage and segment the text into clear question, or it can generate complete answers by consulting a knowledge base, if you provide one. Its behavior always depends on the instructions you set. Fourth pillar is a real-time bridge and real-time agent. This is what turns every text response into speech, not just as plain text to speech, but as a dynamic, adaptive audio agent. When the orchestrator sends a response, the real-time bridge decides whether to use a real-time streaming voice model or a text-to-speech module, depending on scenario and instructions. You can manage and change instruction for real-time model, very simple, through management interface if you need. Together, the bridge and agent ensure no answers overlap. Everything is delivered in the correct order, and every second of audio is under your control. It's important to note that the entire backend is a set of microservices. Each component runs as an independent unit with its own Docker image and clearly defined task, making upgrades, scaling, and maintenance straightforward. Finally, the front-end web and desktop app. The front-end is a modern web application built with Vite and React, available via browser. The desktop or Electron app is for advanced users, offering full control over devices, audio routing, and local privacy of knowledge bases and settings. Deployment of the entire environment, from every backend service to the front-end app, is fully automated with Azure DevOps pipelines. Every update, patch, or expansion goes through controlled versioning with no manual intervention or risk to other parts of the system. The front-end can be hosted as an Azure static web app, giving the users access from anywhere, but it can also run entirely locally via the Windows Electron app. No cloud dependency required. This architecture delivers maximum flexibility, security, and ease of development and maintenance. Plus, gives users the freedom to choose the approach that fits them best. It all starts right here, in my Visual Studio Code environment. That's where I created the entire project structure, both the backend and the frontend, along with all the necessary code. The codebase itself is neatly organized. There's a backend folder for all the core microservices, a front-end folder for the web app, and a desktop directory for the Electron application. Each part has its own dedicated files, configuration, and tests, so I can develop, update, or even replace individual services without breaking the rest of the system. From here, everything else, deployment, configuration, and scaling, becomes way simpler and a lot more reliable. Once my code is ready and all local testing is done, it's time for Azure DevOps to take over. With just a single push to the main branch, automated DevOps pipelines handle everything, building each microservice into a Docker image, running all the necessary tests, and deploying each component to Azure Container Apps for backend and Azure Static Web Apps for frontend. This means that every update, bug fix, or new feature goes live reliably without any manual intervention or downtime. And if I ever need to roll back, I can do it instantly without disrupting the rest of the system. When it comes to security, everything is locked down from the start. All sensitive data, like API keys, endpoints, and tokens, is stored securely in Azure Key Vault or managed as pipeline variables. For this showcase, I built a Windows application specifically to show you as many technical details and data flows as possible. Of course, the final look, features, and user experience, whether desktop or web, can always be customized for any audience or use case. One of the key advantages of this architecture is its total flexibility. You can adjust the model's behavior instantly without touching a single line of code and without restarting any backend or front-end services. It's also possible to predefine instructions for any group of users so that every new session automatically follows those rules. No admin interface required on their side. Need to switch out a model? You can do it at any time, just by changing a variable value in the Azure Container App settings, with no code changes and no downtime. That's exactly why this design is so flexible, making it easy to support a wide variety of real-world use cases. And now, remember how I said noise is a real headache for real-time voice models? That's exactly why I brought in Agent 1, to untangle and clean up those slightly chaotic questions, so our voice model doesn't get confused and can answer precisely. So, let's put it to the test. I'm going to hook up my models and throw in a question that's a bit all over the place, just like real life. Let's see how Agent 1 manages to whip it into shape, and if the real-time voice model can actually give a clear answer.
Hey, so I was trying to place an order, but it kept giving me some error. I think maybe I forgot my password. Oh, can you check if my order actually went through, and is it possible to change the delivery address if it's not too late? Sorry, I'm rambling.
The speech-to-text model grabs everything I said and hands it off to the orchestrator. From there, Agent 1 steps in, filters out the mess, and gives back a clear question. Finally, the orchestrator sends that straight to the real-time voice model.
I will check your order status. Next, I will confirm if the address can still be updated.
See that? The real-time voice model delivers a spot-on answer, even though the question was pretty all over the place. But let's check under the hood and see exactly how Agent 1 transformed that chaotic input into something the AI could work with. See the difference? Agent 1 did all the hard work, neatly rephrasing the question, so the real-time voice model had a pretty easy job answering it.
So let's make the conclusion. Each component is modular, independent, and can be scaled, changed, or restarted without affecting the rest of the system. Deterministic flow: every input-output is auditable and can be reconstructed or reviewed at any time. Security and privacy: all secrets and configurations are protected. The knowledge base can be local or cloud-based, depending on your needs. Flexibility: you can easily change instructions, knowledge base, answer styles without redeploying or headaches. Scalability: you can extend the system to new domains, languages, features without reinventing that wheel. The limits: this architecture is great wherever control, auditability, security are crucial, but this required well-planned DevOps. Clear separation of concerns and disciplines in configuring each service. That was all for this video. Thanks for watching, and we will see again in next one.